So this is a video in which I'll be explaining about what an electrical charge is all about, and we will find what a coulomb what a 1 coulomb of charge is, and then I will define the Coulomb's law and mathematical definition of Coulomb's law. So this video is about defining electrical charge, then defining what Coulomb's law is in the mathematical form. So to define a charge, consider that all the elements is made up of what is known as an atom, and the atom consists of a nucleus which is having a positive charge due to the protons and neutrons here, and the nucleus is being revolved around by the orbits in which there are electrons. So if you consider a simple hydrogen atom, then there will be 2 electrons in the outermost orbit. So these electrons give what is known as, so if there are more number of, so as much number of electrons, there will be protons. So when the protons is equal to the electrons, the atom can be said as being neutral, and when there are more protons, the atom can be said to be having a positive charge or negative charge, or it can be said to having a positive charge. So we say that an electron is an object which has a charge of close to 1.6 into 10 raised to minus 19 coulomb, and the charge of an electron is always negative, and the charge of a proton is 1.6 into 10 raised to minus 19 coulomb positive. So again, coulomb is a unit of charge, and one electron is having 1.6 into 10 raised to minus 19 coulombs. So you can find out what 1 coulomb is by dividing 1 divided by 1.6 into 10 raised to minus 19. 1 electron into 1 electron is equal to 1 coulomb. So by doing that, what you will find is how much number of electrons are needed to produce 1 coulomb of charge. So 1 coulomb will be equal to something like 6. So I will have to compute that. So again, continuing, what you will get is something like 0.625 into 10 raised to 19 electrons, which will be something like 6.25 into 10 raised to, so if you are taking it here, so you'll have to multiply it by 20 electrons. So this is a number of electrons which is needed to produce 1 coulomb of electrical charge. So if you have an object like a sphere, if you are somehow charging this sphere, and if you are putting this much amount of electrons on this, that is a negative charge, negative electrons on this, then you can say that this has a charge of 1 coulomb, and this is a 1 coulomb negative charge. On the sphere which you have somehow removed this same number of electrons, then you can say that it has a 1 coulomb of positive charge. So that's how you are defining a charge. And the next is a Coulomb's law. So what you're doing is that you are mathematically, what we are doing here in this case is we are mathematically defining the Coulomb's law. So if you want to know more about the Cartesian coordinate system and the vector representation, then you should go through the previous lectures. But just assuming that I have a Cartesian coordinate system which is used to represent the position of two charges in space. So I have a x coordinate, I have a y coordinate, and I have a z coordinate, and I have a charge which is a charge q1 here, and this is a charge q2 here, and this a position vector is r1 and the position vector is r2. So this is my charge, which is a stationary point in space. This I have located at this point in space, and I am representing it by two vectors, position vectors r1 and r2. So my resultant vector, so I want to find the force F12, which is a force on charge 1 due to charge 2. So Coulomb defined the law which says that the force in this case will be directly proportional to the charges, that is q1, q2, and inversely proportional to the distance, which is this distance between the two charges. So this will be represented by a vector r12, and this r12 whole square, that is the magnitude of the vector whole square, will, and the direction will be given by the unit vector from the direction of this will be the r21. When we are considering the force on 1 due to 2, we are moving from so again this direction will be given by whether we are considering what you are considering for both these charges. So this is also positive charge and this is also positive charge. So when I am considering the force on 2 due to 1, so the force will be always repulsive and it will be away from 2. So the direction will be from 2 to 1. The direction in this case will be from 2 to 1 when I am considering that this is also positive and this is also positive. So this is a way to represent this Coulomb's law mathematically when I am having 2 point charges separated by distance. And now again, considering the constant in this case can be written as a k q1 q2 divided by the vector r21 in the specific case and the magnitude of that vector or the magnitude of that vector in this case. So again, just so this is how I am mathematically defining the Coulomb's law. So this is a universal law in the field of electrical engineering and was defined by Coulomb. So the scientist who defined was a French scientist and his name was Charles Coulomb, and he did that in the 17th century. So this is a mathematical representation of Coulomb's law, and considering the constant, now just taking the case of considering that we define the Coulomb's law for this case which you see as F is equal to, what we defined was F is equal to K Q1 Q2 defined given by the R21 magnitude whole square and the R21 position vector or unit vector, and this is a vector for the force on 1 due to 2, and we are considering that both is a positive. and again the value of the k is given by 1 upon 4 pi epsilon naught, and this value is found by experimentation of close to be 9 into 10 raised to 9 Newton meter square divided by Coulomb square. So how you find the unit of k is that the k is equal to force, the unit of force. You're taking this simply here to find out the k, and you are having the Newton meter square, the unit of force, and you are having Coulomb square, which is the unit of the charge. So this is Coulomb, and you will square it, and that's how you're finding the unit as Newton meter divided by Coulomb square or Newton meter square. So again, meter square is a unit of this, and the position vector will have no unit. So that's how you have found out the unit of k, and epsilon naught is something like the permittivity of free space. The value of the epsilon naught, which is the permittivity of free space, is found to be 8.85 into 10 raised to minus 12, and the unit is Coulomb square Newton inverse meter square inverse. So again, k is 1 upon 4 pi epsilon naught, so you are substituting that and you can find the unit of epsilon naught easily. So these are the two values which we are defining. These are constants. So through experimentation they found that while mathematically defining the constant, the value will come, and epsilon naught, which is a permittivity of free space, defining in simple terms, is how freely the electric field can move in vacuum. And when you are considering different mediums like a water, air, the permittivity will be different. So again, epsilon, to define the permittivity in another medium, will be like relative permittivity, that is a permittivity relative to the free space. So that is known as the relative permittivity. So if you are considering that the 2 points are, or the two forces which we said like q1 and q2 were acting in free space, then only we will consider the epsilon naught while defining the Coulomb's law. But we are considering that these two charges are in some specific medium like a gaseous medium, then you will have to consider the permittivity of that gas, and that can be defined by adding one more constant known as the epsilon r here, which will be the relative permittivity of that medium with reference to the permittivity of free space. So that's how you have defined the Coulomb's law, and the next is considering and defining the Coulomb's law in vector form. So we have learned the Cartesian coordinate system, and what we will now, this is a representation of Coulomb's law in vector form. So we learned the Cartesian coordinate system, and we know that we can represent anything in space using 3 coordinates, and this is a Cartesian coordinate system that is x, y and z. So I'm having a charge q1 here, so this is my position vector. I'm representing this at this point by a position vector r1, and at the same time I'm representing it here q2 charge by a position vector r2, and this is a positive charge which I'm having, and this is a positive charge, and Coulomb's law is F is equal to k q1 q2. This is a vector, and this is r12 magnitude whole square and r12 whole square. So I'm considering that the force on 1 due to 2, and the specific case where this is positive and this is negative, the force could be in this direction, which is F12. and this is the direction of the force. This is F12, and being more clear, if this is R12, the vector R12, and the force F12 will be in this direction. This is just a representational diagram, not accurate, and this can be written as F12 is equal to Q1 Q2, this is not vector but Q1 Q2 divided by R12 whole square and R12 unit vector. And again, what is my R12? When you are talking about position vector, you will have to remember that R12 is R1 minus R2 and the unit vector R12. So this is how you are defining a vector R12. So that's how you are defining the Coulomb's law in mathematical form, and you're converting, also representing that in the Cartesian coordinate systems. So that was all about Coulomb's law and how you can use that to find out the force between 2-point charges in space. So some of the important things which you will need to consider here, we are defining what we have done is that a force between 2-point charges can be given by k, q1, q2 defined by the r square, which is the distance between, and position vector. And being very specific, this is also a vector quantity, so the q1 and q2 are point charges. When I say point charges, is that they can be considered very small compared to the distance. So when you are having such kind of charges, they are called point charges. So the application of the Coulomb's law is to the point charges, and it is proportional to the distance. So one other thing you can say is that as the charges are, if the charge is high, then the force will be high, and if the distance is higher, the force will be lower. So these are some of the things which you can deduce from the Coulomb's law. And again, this is a universal law in the field of electrical engineering, defined by Charles D. Coulomb or Charles Coulomb. So that's all.